sklearncompose. Description: the sklearncompose module provides tools for building more complex machine learning pipelines by combining different estimators. This module allows you to streamline the process of pre-processing data, selecting features, and building models. Inputs. Data: the input data can be a pandas data frame or a NumPy array. It should be in a suitable format for the specific estimator you are using. Target variable for supervised learning tasks. The target variable should be provided. It can be a single column from the data frame or a separate NumPy array. Outputs. Transformed data: the output will be the transformed data after applying the specified transformations and feature selections within the pipeline. Model: the final trained model is returned, enabling you to use it for predictions. Steps. Pre-processing: this involves steps like data cleaning, scaling, encoding categorical features, and handling missing values. The column transformer class is a versatile tool for applying different transformations to specific columns. Feature selection techniques like feature importance ranking, dimensionality reduction (PCA), ELDA, and feature engineering can be incorporated to improve model performance. Model training: the desired machine learning model, e.g., linear regression, random forest, support vector machine, is trained on the processed data. Metrics. Accuracy measures the percentage of correctly classified instances for classification problems. Precision indicates the proportion of correctly predicted positive instances among all positive predictions. Recall represents the proportion of correctly identified positive instances among all actual positive instances. F1 score: a balanced metric combining precision and recall. Mean squared error (MSE) evaluates the average squared difference between predicted and actual values for regression problems. Visualization plots. Feature importance plots show the importance of different features in the model. Confusion matrices visualize the performance of classification models. ROC curves plot the relationship between the true positive rate and false positive rate to assess model performance. Learning curves evaluate the model's performance as the training set size increases. Fine-tune parameters. Hyperparameter tuning: adjusting parameters within the chosen model to optimize its performance. E.g., using grid search CV or randomized search CV. Regularization parameters controlling the complexity of the model, e.g., lasso, ridge, elastic net. Uncertainty methods. Confidence intervals provide a range of values around a predicted output, indicating the uncertainty in the prediction. Bootstrap aggregation bagging: creating multiple models from different subsets of the data to estimate prediction variability. Challenges and fixes. Challenge 1: data leakage, introducing information from the target variable into the training data during pre-processing, leading to overly optimistic model evaluation. Sample use case that resulted in challenge 1: using a transformer that utilizes the target variable, e.g., scaling based on target values before splitting the data into training and testing sets. Fixes to challenge 1: apply the transformers after splitting the data into train and test sets. Ensure that any pre-processing steps only use information available during the training phase. Challenge 2: overfitting: the model performs exceptionally well on the training data but generalizes poorly to unseen data. Sample use case that resulted in challenge 2: using a complex model with too many parameters or not enough data for the model to learn from. Fixes to challenge 2: consider simpler models. Apply regularization techniques. Use cross-validation to evaluate model performance. Or gather more data. Challenge 3: data imbalance: uneven distribution of classes in the target variable can lead to Biased model predictions. Sample use case that resulted in challenge 3, a dataset where one class is significantly more frequent than other classes, e.g., fraud detection. Fixes to challenge 3 use oversampling techniques, e.g., smart undersampling techniques, or cost-sensitive learning to balance the classes. Challenge 4 handling categorical features. Categorical features may require encoding or one-hot encoding before being used by many models. Sample use case that resulted in challenge 4, a dataset with columns containing text labels or other categorical values. Fixes to challenge 4 use ordinal encoder or one-hot encoder within the column transformer to transform categorical features. Challenge 5 missing values. Handling missing data appropriately is essential for model accuracy. Sample use case that resulted in challenge 5, a dataset with missing values in some columns. Fixes to challenge 5 use simple imputer to fill missing values using strategies like mean, median, or most frequent value. You can also use KNN imputer to impute missing values based on similar data points. Challenge 6 feature scaling. Different scales of features can impact model training, leading to inaccurate results. Sample use case that resulted in challenge 6, a dataset with features having significantly different ranges, e.g., one feature in meters and another in millimeters. Fixes to challenge 6 use standard scaler or min-max scaler within the column transformer to scale features to a common range.